Hey everyone, Sean here for Lambda School, and in this video we're going to be going over the large and very important topic of runtime complexity. We're going to be going over kind of what runtime complexity is, what the point of it is, as well as enumerating some of the main big O runtime classifications that are central to how we talk about runtime complexity and actually making sense of it. So first off, let's look at the question of what's the point of runtime complexity. The point of runtime complexity is that we want a way to essentially compare arbitrary algorithms or functions or pieces of code, which right off the bat, if you're thinking about it, might be a little bit like comparing apples to oranges, right? Because algorithms take in all sorts of different inputs, spit out all sorts of different outputs, and you might have two algorithms that have very little in common in terms of their actual code. So how do we actually bridge this divide? The way we bridge this divide is by using big O classifications. And what big O classifications are, if we look at this graph, is it's simply a graph comparing the input size. So whatever input you might give to an algorithm, we're looking at the size of that input. And we're looking at and asking, as the input size increases, how many operations or how many more operations does the code that we're executing or the algorithm that we're executing need to perform? So here's some of the main big O classifications, and these are the ones that we're going to be enumerating and defining and walking through some examples of. And here they're listed in the order in which the classifications, they're listed in their order of classifications. So up top we have constant time, which is considered the best runtime classification, and then going all the way down to exponential time, which is considered the worst, or say one of the worst. And you also noticed, looking at what's inside the parentheses of each big O class, these are all functions, right? So log n is a function, n is a function, n log n to the power of c for some constant, and then an exponential time, c for some constant to the power of n. So when we're talking about big O classifications, c just is the placeholder for some static constant, so some number that doesn't actually change or is not a function of input size, and then n you can think of as the actual size of the input to whatever algorithm we're considering. So again, as I just said, all of these are functions, so we can graph these out on a graph, and when we do that, we're then kind of able to see the growth of those functions as the number of elements or the input size grows, how many operations some arbitrary algorithm will need to perform for that number of elements. So we see at the bottom that O of 1, in this case, this is constant time for O of some c, so 1 in this case is just a constant, as well as log n are down at the bottom, so they exhibit performance where when the number of elements increases when the number of elements increases, the number of operations that the algorithm needs to perform doesn't increase. Either it doesn't increase in the case of constant time, or it doesn't increase very much in the case of log n. And then up next we have O of n, which is linear time, which basically says that as the number of elements to some algorithm increases, the number of operations grows in direct proportion. And then moving on, we have n log n. After that, n squared, which is called quadratic time, and then 2 to the power of n for exponential. We're not actually even going to be talking about n factorial. So first up, let's talk about the first runtime class, constant time. And again, constant time is when, intuitively, you can think of it as for any input size n, the number of operations that some algorithm that some constant time algorithm performs for that input size does not change, right? So again, for n input size, if we pass that in to our algorithm or our function, the function is always going to be performing the same number of operations to get the job done. And again, in terms of if we were to graph this function out, it would just be a straight horizontal line indicating that the number of operations does not change at all. So some examples of constant time, some analogies that we can come up with. You can think of the first one as, well, when we have like one of those lottery ball machines, we could reach in and just grab a lottery ball, right? It doesn't matter how many lottery balls are actually in the machine. When we just want to pick a random number out of the lottery machine, we just reach our hand in and take one out, right? We could have 2 balls in there, we could have 1,000,000 balls in there, and if we just care about picking a random number, the number of operations we need to do to actually just go and get a number out of this machine is always the same. Similarly, we could also think of like a card house, right? It doesn't matter how large the card house is, it always only takes a single operation, a single misstep, for the entire card house to come crashing down. Again, the card house could be really small, it could be the biggest card house you've ever seen, but it doesn't matter. It takes one mishap, or one operation in this case, to literally destroy the entire thing. To use some more programming related examples, we know that when we have elements inside of an array, we can always go and just fetch some element in the array via its index. So if we know the index up front, we can just use that to directly access the element stored at that index, and that always takes the same number of operations. It doesn't matter how many elements are in the array. Again, as long as we know the index, we can just go and fetch that element, right? And it's the same thing with hash tables or objects from JavaScript or dictionaries in Python. I'm going to be using the term hash table because that's more language agnostic. So again, hash tables are just objects in JS or dictionaries in Python. But we know that with a hash table, we could have keys and values stored in a hash table, and we can always just use the key to go and fetch its associated value from a hash table. And these are true because of the way the data structures, right, arrays and hash tables, how they organize the data. So once you actually insert the data into the array or the hash table, it's already indexed, again, by some index in the case of an array, or by the key in the case of a hash table. And so when you want to go and fetch that same element again out of the data structure, we're just essentially telling the data structure exactly where to go and pick that element up. So let's look at some code examples. Here in this one, we'll just have this function called print the 100th element of some input array. And assuming this array has that many elements, if we just go and print out array with the index at 99, that is always going to take the same number of operations. Again, it doesn't matter how many elements are in this array. If we want to just print that element out, we just go and we'll just fetch that element straight out of the array at the given index and then print it out. Similarly, if we can look at this function called loop 50 times for some given array, in this case, we're just looping from I starting at 0 up to 50, right? So in this case, we're always performing 50 prints, right? So again, doesn't matter. This function, the number of operations that this function is executing does not at all depend on the size of the input array. It's always just going to be looping 50 times. So even if we had loop 100 times, 1,000 times, 1,000,000 times, even though that might be a lot of operations, right? 1,000,000 is still a lot of operations, but if the number of operations is just static, even if it's really large, it's still considered constant time. Okay, let's move on to the next one, talking about logarithmic time, or log of n. And we can guess, or we can see that in this case, the number of operations is going to grow as a function of, as a logarithmic function of n. But intuitively, you can think of it as, again, that as n increases, as the input size increases, the number of operations is not going to grow very quickly, because the function log n essentially tapers off. So as n gets really, really large, log n is not going to increase by very much. So this is kind of the next best thing we can get after constant time. Let's look at some examples or some analogies. So it turns out when we're looking for some entry, like through a dictionary, right? So if we're looking through a dictionary and we're looking for a particular entry, we don't need to go and open up the dictionary to page 1, look at all the entries in there, flip to the next page and look at all the entries in there, and keep going until we find the entry we're looking for. Because we already know how a dictionary is organized, and we know for whatever entry we're looking for, we know roughly where it is in the dictionary. We might not know the exact page that it's on, but we have a pretty good idea. And so actually, intuitively, you can imagine this as, because we have a general idea of where the entry is that we're looking for, we're able to bypass a bunch of pages of the dictionary that we just know that our entry is not going to be in. Right? It's kind of similar to if we imagine a bunch of books on a bookshelf that are ordered alphabetically. Again, kind of the same thing, right? We know generally, if we're looking for a book and we know its title, we'll generally have an idea of where that book is. So if our book starts with the letter G, we don't need to go and look in the A section because we know it's not going to be there. We're not even going to bother looking. And so kind of the programming equivalent to this idea that we have a general notion of where the element or the entry that we're looking for exists is called binary search. And this particular algorithm crops up a lot. It's especially useful for when you want to look for some element or some entry in some data that's already sorted or almost sorted. And just to give some code example, here's some pseudocode for a binary search algorithm that receives a sorted array. So the data in the sorted array is already sorted, and then some target element that we're looking for. And the way binary search works is we typically want to start off by finding the midpoint of our sorted array, and then we're going to compare the element at the midpoint with the target. And so if it matches, then cool, we've already found the element we're looking for. But if it's not the one we're looking for, then we know if the target is less than the element at the midpoint, we don't need to now go and look at the other half of the sorted array, because the other half of the sorted array is going to be containing elements that are larger than the element at the midpoint that we just looked at. So we now know from that check, we know that if the element that we're looking for in the sorted array does exist in this sorted array, it's going to be on the left side, the side where the elements that are smaller than the midpoint are. Conversely, the same is true if the target ends up being larger than the element at the midpoint. We just need to go and look at the right side of the sorted array. So it's kind of the idea. The idea then is that when we're doing comparisons, we're able to basically reduce the amount of work that we need to do, right? We don't need to go and look at every single element in the sorted array, again, because we have a general idea of where the target element is going to be in the sorted array. And just to again show the graph of the function log n, we see that it starts off, when the input side is really small, it starts off with a pretty high growth, but then as input size gets larger, it tapers off. So even when input size is very, very, very large, the relative number of operations is not going to be nearly as big. So again, this is kind of the next best thing we can get after constant time. Okay, let's move on to linear time. And again, linear time is where the number of operations that need to be performed as a function of n is a linear function, or in other words, the number of operations that we need to perform for some given input size grows in direct proportion. So for example, we might have some input size n. If we add one more to n, so if we go from n to n plus 1, we might have to increase the number of operations by 1 in direct proportion. Although it could also be some other proportion, not just 1 to 1. So any sort of linear constant proportion. And the graph for that would just be a diagonal line, and its steepness might fluctuate depending on, depending on the proportion. It might be a low proportion, in which case the line could be almost flat, or it could be a really, really steep proportion, in which case the line would be shifting more to the left and still increase really quickly. But it's always just going to be in direct proportion. So you can think of it as there's not going to be any secrets here. So as far as examples of linear time, kind of the most obvious might be just counting. So if you're counting something, like for example, if you're counting marbles or you're counting coins, you need to look at every single coin. So you see a coin, you'll add one to your counter or your fingers or whatever, look at the next one, add one more, etc., etc. So we need to look and scrutinize every single thing that we're counting or everything that we're inspecting. Right? You might also imagine if you have 11 dogs and none of them want to get in the bathtub with each other, then you're going to have to go and wash every single one of them one at a time. So looking at some code, here's an example of a search algorithm with some given array, and in this case the array is not sorted. So we don't know anything about the elements that are already in the array, in which case we cannot use a binary search because we don't have any knowledge going in of where things are going to be in this input array. So in this case, we don't know how the ordering of the elements that are in the array. We're going to have to go and do a search by literally inspecting every single element one at a time. Right, so in this case, we can look at the code and see that it's doing a for loop over every single element in the array and then just checking to see if this element that we're currently looking at matches our target. If it does, we'll return true. Otherwise, we get all the way through the array and none of them matched, so we know then that the element we're looking for is not in the array. Next up, if we had a function like this, again, some function that's given an array and it's all just going to print all the elements twice, right? In this case, the proportion is not 1 to 1 because we have more than just one for loop for every single element in the array. But in this case, we're just doing two things per element in the array. So in this case, the proportion is not 1 to 1. So it comes out, the actual runtime classification would be 2 times n, but that's still considered constant time because the 2 in this case is static, right? So the 2, or the number of things we're doing per array element does not depend on the input size, right? So in this case, we're always just going to be performing 2 operations or 2 actions for every single array element. And then next up, so far we've had examples where the inputs were always arrays, but that might not be the case, right? So if in this case we had just n as some integer, that works perfectly fine as well. So if n is just some integer, then that would just be n our input size. So if we were to then loop up to the integer n and then print each index as we do that, that's still basically the same thing. The number of loop iterations that we're performing is in direct proportion to the size of n. So if we went from n to n plus 1, that would add one more iteration to our for loop and would have us print one more additional element. All right, next up we have what's called log linear time, and this was that n log n function. And so again, the number of operations is a function of this function n log n of input size. But intuitively, you can think of this as when we need to kind of look over all the elements that we have, and we need to do some additional work on each one that is dependent again on input size. So it turns out that this particular classification, log linear time, is a little bit niche, and it's mostly only applied to a single type of problem. And that problem is sorting, right? So for example, in this case, we'll walk through an example of sorting some billiard balls. And this would, and just imagine, you're actually doing this yourself by hand manually, right? So if you have a bunch of billiard balls in front of you and you wanted to just sort them by the number on the ball, the way you would do that is you would look at every single ball, right? We do need to inspect every single ball. We just need to see what it is we're working with. And then you would see, hey, 2 is the one that needs to go after 1. Let's go and pick that up. Let's move that over to where it needs to be, and then we need to shift every other ball after it off by 1 so that we have space for the 2 ball, and then we'll put that in, right? So we needed to initially look at what we had to work with, right? So we did have to go and do a scan of every single element, and then the log n represents the additional work that had to be done in order to actually take that element and put it where it's supposed to be in the total ordering of items. So intuitively, again, that's how you can kind of think of the log linear time runtime classification. And again, it's pretty much only applied to sorting algorithms. As far as the actual graph, this is kind of what it will look like. It is a slightly sloping upward diagonal line. So this is where we finally start to see the number of operations is now starting to overtake our input size n. And again, as I just said, log linear time is pretty much reserved for being applied to sorting algorithms. And so far, it's pretty much the gold standard for sorting algorithms. So all of the kind of the most efficient or most effective sorting algorithms, like the ones listed here, quicksort, merge sort, heap sort, and tim sort, are all these sorting algorithms exhibit the n log n runtime classification. Okay, next up, let's talk about quadratic time, and this was O of n squared, or O of n to the power of some constant. Now we're really starting to see that the number of operations starts to increase rather quickly compared to the size of the input, right? If we can just plug some numbers into the function n squared, and we know that when we do that, so for example, if n is 10, n squared is 100, and then if we were to just add 90 additional elements to our input, all of a sudden now we need to perform 1,000,000 operations, right? So it's a very lopsided proportion here now that we're starting to see. And the graph confirms that, right? Because the graph now really starts sloping upward at a very fast pace. And it starts to get unwieldy and clunky, and input size doesn't need to be particularly large before we start to possibly overrun our machine. But some examples of quadratic time might be, for example, when we want to enumerate all of the possible permutations of some string. So in this example, we have a string with 3 characters, and if we wanted to, again, enumerate all the possible strings, it turns out there's 3 squared total permutations, right? So 9. There are 9 possible permutations we could create with this string, and so 3 in this case is n, and should be n squared, because we have 3 things in our string, 3 characters in our string, and then square that for the total number of permutations, for up to a total of 9. So we would have to perform 9 operations in the case of this this algorithm. And then another example would be this sorting algorithm called bubble sort, which is one of the simplest sorting algorithms, because the way it works is it looks at a single element and then it just keeps kind of moving it along, and at each time it moves it along, it compares the number of it compares the number behind it and sees if it needs to swap. And it'll just keep doing this all the way until that one element is in the correct spot. So, and then once we've done that, once that one element is in the correct spot, now we need to go and move on to the next element. So we're literally having elements move through the entire array for every single element in the array. If that doesn't make sense, then we'll show the code in a second. But another example, so here's the permutation example, right? So if we're given an array and it's called print all pairs, we'll see that we have nested loops here. And nested loops are a very kind of rule of thumb you can use to determine if the algorithm you're looking at is displays a quadratic runtime, right? So in this case, we're looping through every item in the array in the first outer loop, and then inside of that we have another loop that loops through the array again for every single item in the array. Right, so if we were to add an additional element to the array, there's a whole that's a whole other inner for loop iteration. The inner for loop would have to run all over again in this case. And then we can also see here the code for bubble sort, which again also has nested inner arrays. And again, that's because it's checking each element once, putting that one in the correct spot, and then it needs to do that for every single element in the array. So bubble sort is not a particularly efficient sorting algorithm. There's not many use cases where you'd actually use it, because again, it exhibits considerably worse runtime than the other sorting algorithms that we mentioned earlier on, namely quicksort, merge sort, heap sort, and tim sort. So those, again, exhibit kind of the gold standard runtime classification for sorting algorithms of n log n. And now moving on to the last runtime complexity. This one's called exponential time, and it probably doesn't need to be said at this point that, you know, the number of operations that need to be performed as input size is increasing is just extremely limiting. And indeed, this is kind of where the edges of what our computers can do sits at. But again, intuitively, you can think of exponential problems as, so we just saw with quadratic time that we had nested loops. But at least with those nested loops, in those examples, the actual number of nested loops didn't actually change, right? When we added additional input, the nested loops just needed to run more times for more elements. But in the case of exponential problems, as n increases, it actually increases the entire number of nested loops, right? So just again, kind of see that in visual form. On the left here, we have a drawing that kind of showcases or kind of diagrams an example of a quadratic runtime algorithm. And in that case, the total number of actions that each loop is performing is dependent on the input size n. So again, if we add more elements, if we increase n, the number of things that these loops has to do increases, but the number of loops themselves always stays static, and that's not a function of the input size n. Contrast that now with an exponential running time function, where it's actually, even though the number of things that each loop does might be constant. It's not dependent on n. What is dependent on n is the total number of nested loops. So if we add an additional element n to our input size, now all of a sudden we would have to add an entire additional nested loop. And that obviously then gets extremely unwieldy and really, really quickly in terms of how many operations our machine needs to compute. So this would be the graph, and it's almost going to be going straight up at this point and going off and off and off really, really, really quickly. Despite the fact that C itself, the actual number, is a constant, but that doesn't, it quickly becomes overtaken by the fact that n would get really, really, really large. So what are some examples of exponential time problems? And it turns out there's a lot, and this is actually where a bunch of interesting problems are actually considered exponential time. So for example, cracking some unknown password is an exponential time problem, because if, for example, if we think, there's a password that we know is maybe 3 characters in length, I should say, if we're trying to crack a password that's 3 characters in length, we'd have to loop through, for the first character, all the possible characters it could possibly be for that one spot, and then we have to do that for the second character and then the third character, and then all of a sudden we realize, hey, instead it's actually 4 characters long. Now we need to add a whole other nested loop that's now again looping through every single possible input character that it could be for that password. And some other ones now include things like the knapsack problem, prime factorization of large integers, and the longest common subsequence of strings problem. And there's a whole bunch more, and all of these problems are, or I should say, we don't really have an efficient way of solving these for large inputs. Surely we can solve them for small input sizes, but as the input sizes for these problems gets even just to a point where they're kind of realistic, it's already too large of a problem for our classical computers to handle. Although that being said, what's nice is that we've taken advantage of this fact, right? So prime factorization of large integers, the fact that this is a problem that classical computers are not able to solve in a timely fashion, is what allowed us to basically construct the whole field of cryptography, and thus kind of, the whole field of security kind of sits on top of that. So if in the future prime factorization of large integers was suddenly solved in an efficient time, much faster than it's currently able to be done, then the entire field of cryptography would probably collapse around our ears, and then some sort of chaos would definitely ensue as a result. Okay, I have a few more things to note before we end the video here. So we kind of alluded to this earlier, but I didn't mention that, well, I didn't explicitly mention, but I'm mentioning it now, that when we come up with some runtime, so when we're evaluating some algorithm, what's nice about Big O is that it allows us, or it gives us the wiggle room to drop constants. So for example, if we were looking at some code that showed or exhibited 5 loops, one after another, that none were nested in, that would come out to 5n because there were 5 non-nested loops. But then when we actually are figuring out the runtime for that, that would just come out to O of n. Because we don't really care about the actual 5 constant in this case. And this is true for any constant, right? So it doesn't matter if it's 5, it doesn't matter if it's 1 over 2. We just get to lop off that constant, and it's all considered O of n. And then this also holds true for terms that are smaller than the dominating term. So in this case, if we calculate some runtime like the following here, with this n cubed plus 1/2 n plus 101, for example, this would just approximate to O of n cubed, and you wouldn't be wrong in just putting O of n cubed down, even though I guess pedantically speaking, you'd be a little bit more correct or specific to enumerate out the non-dominating terms as well, but technically speaking, you're perfectly correct in just saying some runtime like this would just come out and simplify down to O of n cubed.